This is an introduction to geodesy, coordinate systems and projections. Under geodesy, we'll talk about geoid and ellipsoids. We'll talk about surveying, measuring the Earth. We'll talk about datums, for which we need a reference point and an ellipsoid. And we'll talk about projections, for which we need both a datum and a projection. This is latitude and longitude of a point. It could be just outside here on the grass. Is that a unique position? Can you go and walk to that point now? Hands up those of you who think you can walk to that point. Stephanie says if she has a GPS. I'll give you a GPS. Can you go and walk to that point? Hands up those of you who think you can walk to that point. Hi, I need to see this one. It's not very far away. I'll show you where it is on Google Earth. No, you can't. I have not told you in which reference system you are working. You don't know if that's WGS 84, WGS 72, or calculating, or any other datum system. So you cannot walk to that point. That is the fundamental problem, because typically we get lots of data and we don't know in what system it is. And if we don't know what system it is, it's a bit of a pain actually trying to find out. So, how do you actually tell someone where you are? Where did you collect your samples from? Can we revisit the site to go and take more samples for QA and QC? What's your reference system? And that's what this is about. So geodesy is concerned with the science of the study of the shape and size of the Earth in the geometrical sense, and with the study of certain physical phenomena like gravity, which Stephanie is much more involved with than I am, in seeking explanations of fine irregularities in the Earth's shape, and it's intimately linked with surveying and cartography. For my sins, I spent 7 years as a surveyor before I did geology, which is why I end up doing this course. Surveying is the measuring of the Earth's shape and size. Where are we? Cartography is the depiction of the Earth in terms of maps. We are here. Surveying methods. We have triangulation. And I'm taking you back to the sort of pre-GPS days. Yes, I'm that old. And measurements of angles by triangulation, and you all remember SOHCAHTOA and Pythagoras, and being able to calculate positions from angles. Trilateration is the measurement of distances. So as opposed to measuring angles, we can measure distances. Although typically angles and distances were measured, which made things, you had redundant observations and you could assess errors in that. With satellite systems such as GPS or GLONASS, or the European version now, we also measure distances. GPS is a trilateration methodology, it is not a triangulation methodology. That is a mistake you will see in many books, because it actually measures distances based on the Doppler effect. The change in frequency as you get closer or further away from somewhere. So knowing where the satellite is and your GPS receiver in your hand is actually acting as something that is measuring the distances constantly between the satellites and therefore averaging the position that you are at. Consider what we did before we had GPS or satellites. And some group of colonial people went to some island and they wanted to make a map of it. What they ended up doing is creating a baseline first, with 2 points which had direction and a distance along that baseline. And so let's start at 0, 0 here, and that you can obviously sort of, in your imagination, draw in the lines for a triangle, and the baseline was that distance and a direction of 040 degrees. And that enabled you to calculate the coordinates of the unknown point. You can then add in more stations, more survey stations, and you can measure more angles, and you can form a triangulation network. And our first set of triangles we refer to as a primary triangulation network, and of course the next set will be a secondary triangulation network. And so you cover the country or island with a network of triangles. But what you have to remember is that that all falls back on that baseline. If your baseline is not measured accurately in terms of distance and bearing of that baseline, the rest of your network is going to be in error to some extent. This is a picture of the network involving South Africa's first survey from Cape Point, Cape Town, up to this area here, wherever that is. And it was carried out in sort of 1814, 1848. It then developed into South Africa's primary triangulation network, and you can see a series of triangular sort of chains going across the countryside. We then had the trig infill, the secondary and tertiary triangulation networks, which then populated the countryside with trig points, or trigonometrical stations. At the same time, 1800 to 1870, the longest measurement of the Earth's surface was attempted by the Trigonometrical Survey of India, which had these chains of survey lines right from the south of India up into the Himalayas. And these are the sort of tools that we used. Theodolites. And think about back in the 1800s how accurately they could make a theodolite that you could actually read to 0.1 of a second of arc. This is a modern total station, which is very much more digital and much, much more accurate and reliable. This is actually a South African invention by a guy called Dr. Wadley, and it's something called a telorometer. This was his original invention. This is used in a survey in, I think, America, and it measures distances by looking at the change in phase of microwaves. And it revolutionized surveying, because we then went from being able to measure angles accurately to measuring distances very accurately. And in fact, in 1984, in the Himalayas, these are a group of my colleagues then, that is a MRA5 telorometer, that is a mirror used for signaling, and there is a theodolite. And this is at about 17,000 feet in the Himalayas. So that's a sort of brief overview of the classical surveying. It's important to know what a geoid is, and if you've done geophysics, this is sort of nothing new. The surface that would be assumed by the undisturbed surface of the sea, continued underneath the continents by means of small frictionless channels. So it's a bit of an artificial sort of conceptual entity, the geoid. It's not something you can really go and say, oh look, I'm standing on the geoid. Very difficult. An ellipsoid, on the other hand, is a smooth, mathematically defined surface that best approximates to the geoid in the area of interest. And because it's a mathematical figure, we can define it by its semi-major axis, its semi-minor axis, flattening, and eccentricity. Although typically we just use the semi-major axis, 1 over flattening, and eccentricity squared. And you will see tables of ellipsoids. This sort of tries to illustrate the difference between the geoid and ellipsoid. Here we have topography with mountains and seas, and a slightly uneven geoid, which will be slightly higher in the mountain ranges and slightly lower where there are oceans, typically. So our geoid, this is obviously exaggerated, is not coincident with a mathematical ellipsoid. But for any one area that you're looking at, you try and use an ellipsoid that is the best fit to the geoid. A is our semi-major axis. There's the major axis of the ellipsoid. A is half of it, hence semi. And there is the semi-minor axis, which is half of the minor axis. We have an equatorial plane, and we have a north and south pole, if you like, about which we can consider rotating our ellipsoid. It leads to some interesting issues. The ellipsoid we can think of as having lines perpendicular to it, which we call the normal to the ellipsoid. But if you take a tripod into the field, if you take a plumb line into the field and drop something, I take my pen, the path of that pen is defining the perpendicular to the geoid, because the geoid is defined by gravity. So when I drop something, or when I have a plumb line, then that is perpendicular to the geoid. So we define, when we set a tripod up, our position in terms of geoid and spheroid by geoid, but we actually have to do lots of measurements on the normal to the ellipsoid, because the ellipsoid is something we can calculate on, whereas the geoid is much more difficult. Many ellipsoids have been defined. There are global ellipsoids, such as WGS 72 and WGS 84. You will be all familiar, I hope, with WGS 84, the fact that it exists. Whether you know what it is or not is something else. So WGS 84 is a global ellipsoid system. We have a local limited area ellipsoids, perhaps for the UK, which uses the ARI 1830 ellipsoid. For the Indian subcontinent, we use the Everest 1830 ellipsoid. That's how he pronounced his name. So Mount Everest should be called Mount Everest, really. We also have things like the modified Clark 1880, Clark 1866, and Bessel if you're in Namibia. These are all used in southern Africa. They are all different mathematical surfaces. So if you're doing computations on one mathematical surface and you think you're on another one, you're not going to be in the right place. This just gives you an idea of A, B, F for Everest, Clark, and WGS 84. In a lot of cases, they're not that different. Or at least they don't seem to be that different in magnitude, but they do make a difference when you're doing the calculations. So the next thing to understand is, okay, we know what ellipsoids are, and they best approximate to the geoids. So we then have a datum which takes a particular ellipsoid or spheroid. An ellipsoid is two-dimensional, a spheroid is three-dimensional, to a national or international coordinate system. So to define a datum, we need a reference ellipsoid, Clark 1880, WGS 84, WGS 72, whatever, and an initial point. And datum are not necessarily geocentric. We don't necessarily take the sort of centre of the Earth as our initial point. It can be a point on the surface of the globe, at which point we assume that the ellipsoid and the geoid are in the same place. Many datum have been defined. In South Africa, we use Cape datum, and we also use WGS84 datum. In Namibia, I can't remember what Namibia is. Can you remember, Jennifer? Oh, okay, we actually want to use the South African. You use the South African one as well. Okay. In Madagascar, they have a datum called Laborde. In Mozambique, they have 3 different datum depending on where you are. So, in fact, if you're in the north of Mozambique, you'll use a different datum to if you're in the south of Mozambique, if you're using the older systems. And adjacent countries may use the same ellipsoid, but they may have different initial points. The initial point for South Africa is actually down near Port Elizabeth. If you're using Cape datum, you're using WGS84 datum, it's the heart of the Earthquake satellite station, which is not far away from here in the Michalisburg. And at the initial point, geoid and ellipsoid are coincident, and we have 2 important datums, Cape datum and Hartbeespook 94, and of increasing importance is WGS84 datum, which is extremely similar to Hartbeespook 94. Cape datum. Now, I apologise to those of you from places like Zambia, South Sudan, Botswana, Zimbabwe. You will have to think about applying this to your own country. I am going to focus for this lecture on South Africa and an international system. But I could probably do something very similar for each country as long as I sort of had the time to go and find things out. Cape datum was used in South Africa. Some people still use it, and historical data will still use it. Modified Clark 1880 ellipsoid and uses the Buffelsfontein trig beacon as an initial point, which is down near PE. The Hartbeespook 94 datum uses WGS 84 reference ellipsoid and the Hartbeespook radio astronomy telescope initial point, which is in Michalisburg. If you only have a datum, you can only use geographical coordinates. Geographical coordinates are latitude and longitude. And we have parallels of latitude, which are concentric circles, and we have meridians of longitude, which are great circles, each of which are the same length, whereas the latitude parallels vary in length depending on whether you're near the equator or near the poles. Height is more of an issue for geophysicists than it is for geologists. We generally, as geologists, don't worry about it too much because you can have an orthometric height, which is perhaps a height above mean sea level or a height of your topography. You can have a height which is an ellipsoidal height, which is from the ellipsoid to where you are, or you can have a height which relates to the geoid to where you are. So when you say, how high are you? A pedantic surveyor will ask you what your reference system is. But most of the time, we can get away with thinking about orthometric height, which doesn't change too much depending on which ellipsoid you're on. This is just a diagram to make sure you all know about latitude and longitude, which I'm sure you do, but I think I need to keep it in there just in case. So those are latitude, those are longitude. We have 90 degrees and minus 90 in terms of latitude. We have 0 to 180, minus 180 and 0 to plus 180 either side of the Greenwich meridian. Latitude negative south, positive north, longitude 0 to 180 east or west. Typically negative west, positive east. That is convention. So, the next question is, you might think about this a little bit before putting your hand up, is 1 degree of latitude the same as 1 degree of longitude in terms of distance? If not, which is the longer or which is the shorter? Have you thought about this before? Is 1 degree of longitude the same as 1 degree of latitude? Yes or no? Good. So, at the equator, in fact, it approximates to the same. But as you go up here, you can see that your longitude distance between this line at 0 and this line here, whatever that is, it's that distance there and that distance there. At the North Pole and at the South Pole, longitude doesn't really exist. Because if I hold and I spin round, I'm going through 360 degrees of longitude. Okay? So the distance that a degree or a second or a minute of longitude arc subtends varies with your distance from the equator. So that is one reason why if you draw a grid with latitude and longitude, your distances should not be the same on the x-axis and the y-axis. And it makes it really annoying to try and measure it with a ruler. Okay, we don't necessarily do that anymore, but you must be aware that if you're drawing latitude and longitude, or if you're measuring latitude and longitude on a big enough scale, your distances should be different. This just gives you the difference between orthometric and ellipsoidal height, and we have the geoid here. Can I get it right? The geoid, the ellipsoid, height with respect to the ellipsoid is ellipsoidal height, little h. Height with respect to the geoid is orthometric height. K is something called geoidal separation, and it's the distance between the ellipsoid and the geoid, which the ellipsoid could be below the geoid or it could be above the geoid. Depends on where you are in the relationship between your ellipsoid and geoid. And that really gives you the definition of those three terms. Orthometric height, gravity-defined vertical. Geodetic height, we cannot measure directly because it's from a mathematical surface to the point where we are. And when you're standing on the surface of the planet, you don't know where your spheroid is, really, unfortunately, or ellipsoid. So, that's latitude and longitude. We then have to think about projections, because we want to actually produce a map that's flat. And this has been a problem ever since people started drawing maps. You can go back and look at the history, and you can see all the different sort of methodologies that people use. But projections are a way of displaying the Earth's surface, which is relevant to the geoid, onto a planar surface, a map, using a datum, a reference point, and an ellipsoid. And there are many projections, as you will see in a minute. And which one is used depends on the requirements of mapping, or what you want to do with the map, and what you want to do with the projections. All projections are problematic. They do not preserve all features uniformly. Distortions make geoscientists sad, S-A-D-D, because they will distort shape, they will distort area, they will distort distance, and they will distort direction. Some projections are better than others, and in particular, the UTM projection does not distort direction as much as other projections. It still distorts shape, area, and distance. You've come across UTM? Yeah. UTM, Universal Transverse Mercator. Mercator was a guy who lived somewhere in the sort of 1700s or 1800s. He devised a system which we now call, has been called since his day, the Mercator projection. And the primary reason he wanted to do something was because he wanted to give the sailing ships the ability to sail along a straight line on the curve of the Earth. But he wanted it to be at a constant bearing, a constant angle from his compass. Because that meant they could sail from the UK to America along a particular direction and know that they were going to end up in New York instead of Florida, or vice versa. So that was the reason for Mercator's projection. There are many types of projection. We can have conformal, equiangular, equidistant, azimuthal, which maintain different aspects. So conformal projections maintain shape, such as the Lambert conformal conic projection. An equal area projection maintains area, such as the Albers equal area conic. We can have an equidistant projection, which preserves distance, which gives us an equidistant conic projection. And we can have an azimuthal projection, which preserves direction, such as the Lambert equal area azimuthal. You do not need to remember all of that, because essentially there are only really 7 projections that are used, or varieties of them that are used worldwide. And I suppose to some extent this is a colonial legacy, but it affects the whole world. It's not just sort of Africa. It affects Australia, South America, North America, and everywhere else. And so in red are places that use the universal transverse Mercator projection. And you can see that dominates in most of the planet. The other one is a variety of UTM projection. And I put that down as other versions, and you can see that South Africa and Namibia both use a sort of different version of the UTM. Australia also uses a different version. In some ways, it's also related to the shape of the country. If you have a long north-south country, like, let's say, Peru or Chile, you may want to have a very different projection from perhaps the United States, which has a much greater east-west extent than north-south extent. And so projections are not just the best fit for everyone, but in some cases, in America where they use a polyconic projection, it's related to the shape of the country you're interested in. So the most common projection, UTM, stands for Universal Transverse Mercator. There are 6-degree wide zones. It extends from 84 north to 80 south. It is not symmetrical about the equator, because there is more land mass in the northern hemisphere than there is in the southern hemisphere. Yes, it's northern hemisphere centric. It uses the international meter. One reason why Namibia is not quite a UTM projection is because in the past it used the German legal meter, which is different from the international meter. So you need to be aware which meter you're using. In South Africa, there are things called Cape feet, which are different from imperial sort of British feet, which are different from American feet. And so to actually convert between these is a problem. It's a pain. But the typical UTM uses the international meter. The origin of the projection is the intersection of the central meridian and the equator. We have eastings at that origin. So this is really, if you imagine a sort of XY graph, and you've got positive X to the right, negative X to the left, positive Y to the top, negative Y to the bottom. The origin is at the intersection of the central meridian and the equator, so that's where your sort of 0, 0 point is on an XY graph, but it's 500,000 meters east, so that we never have any negative values within our UTM zone. We never have a negative east value in a UTM zone because at the origin we're at 500,000 meters east. In the southern hemisphere, we make that origin 1 million meters because that again means we never have any negative numbers if we're in the southern hemisphere. If we're in the northern hemisphere, we have a northing of origin of 0 meters. The obvious question here is what happens if you have a country that goes across the equator? And in fact, your coordinates will change as you go across. If you are using a consistent UTM in that country. However, if you use your own slightly different UTM version, you may end up with zones which give you positive numbers wherever you are. I'm not exactly sure what Uganda does, but certainly Uganda is an example of a country where the equator goes right through the middle of it. I ought to look at that. Scale factor of origin is an interesting point because you might come across this figure. If you have a standard UTM zone at the origin, you could perhaps take a distance measurement, let's say a kilometre, and you could compare that with the length on the ground to the length you say it is on the map using your projection. And in fact, that is termed the scale factor, and in the UTM system it's 0.9996, which is reasonably accurate for distance. And here we can see that diagrammatically. That should be 1 million rather than 10. There's 500,000 million east for our x-axis. There's the equator. 30 degrees east. 33 degrees east is our central meridian. And we have 6-degree wide zones. And in fact, that's UTM zone 37. Note that the UTM zone number does not relate or correspond to either the western margin of the zone, the eastern margin of the zone, or the central meridian, which can confuse people in certain cases. So the UTM zone number does not relate to any longitude figure. We then come to something called the Gauss conform, or LO projection, latitude of origin, which is used in South Africa. And we have a southern hemisphere here, and our vertical axis is X. Our vertical axis is not Y. Our horizontal axis is Y, and not X. Our vertical axis going down is positive from here downwards. Our y-axis is negative to the right and positive to the left. So it's a bit like a normal Cartesian graph in reverse. You can imagine that computers don't like that, or at least didn't like that, when they were used to using sort of normal Cartesian equations and normal Cartesian geology. So it's a zone that starts at the equator and goes down to the South Pole.
Is that a reason why many modeling software use negative values for
the way companies get around it is that obviously a lot of the modeling software has been developed not in the southern hemisphere, although some of it might have been developed in Australia, in which case they use a different projection but with normal positive and negative. Companies get around it in several ways. They ignore the negative x and will multiply everything by minus 1 to give them a positive number. Also, because they don't use a false easting, there are different ways in which they get around the numbers on the horizontal y-axis. You can just add or subtract a factor. And so some companies will add a large number to it to make everything positive. But if you're dealing with all of this, the thing to do is to write down somewhere what you are doing and what you have done. And the other thing to do is talk to the surveyors and make sure you know what they are doing. Because if you want to then get someone to do a geophysical survey, what coordinates are you going to ask them to give you? Are you going to ask them for what's on your system historically? Or are you going to ask them to give them what they normally do, perhaps from the GS 84 UTM, which they used to do, and you're probably confident that they can do that. If you give a geophysical company a complex projection to give you the data in, they may or may not be competent at doing that. Would you generally agree with that? Thank you. Generally. I think the international geophysical companies, the sort of Fugros of this world, are very well aware of different datums, different projections. But if you've got a company that's working virtually 100% of its time in one country, and you then want them to go somewhere else and do a survey for you, you may need to sit down with them beforehand to make sure that you're all on the same page. So, there's a little summary diagram, Y along the top, X down there. It also gives us a difference between something called a grid and a graticule. A grid is the XY coordinates on the projection. A graticule is the latitude and longitude of slightly curved lines. So the LO system, LO stands for latitude of origin. The width of the zone is different, about 2-degree wide zones, which actually results in perhaps less distortion. Used in South Africa and Namibia, it uses the international meter in South Africa, or historically it has used the Cape Foot, or in Namibia it has used the German legal meter. Its origin is the intersection of the central meridian and equator, and the origin is 0, 0. They do not use false eastings, which gives us negative numbers the wrong way, i.e. to the right, as you think of it in terms of Cartesian geometry. Scale factor at the origin is 1. Right, I'm going to explain something. I'll try and do it visually. I'll try and put this into a PowerPoint at some point, Stephanie. We'll modify it. You're going to try and record it. That might not be an idea. Imagine this block of rock is the Earth. And essentially, for any projection, what we're doing is putting a flat surface close or to the Earth, and we're projecting either from the centre of the Earth to the paper, or somewhere on the paper back to the Earth, or from the other side of the paper into the Earth as well. What the LO system does to get that one scale factor is it actually has its piece of paper right on the edge of the curve of the Earth as a tangent to the Earth. What the UTM system does is says, no, that's not quite accurate. What we're going to do is take a little slice through the Earth, and that's where we're going to put our piece of paper. So, in fact, that negates, in some ways, the amount of distortion you get in a 6-degree wide zone compared to the amount of distortion you get in a 2-degree wide Just because you have a wide zone doesn't necessarily mean that you're going to get more distortion than a narrower zone. It depends on where your sort of projection projects from and to. So here's a diagram of the LO zone 33. In this case, LO zone 33, the number reflects the central meridian, which is actually, I think, quite a good thing. You know where you are. There's minus y plus x, 32 east, 34 east. And most of us in South Africa, Namibia, are used to using LO zone 33 or LO zone 34. That is a comparison between two datums, either the Hartebeest-Hoek 94 datum and the Cape datum. And so if you are using the Cape datum, you are using those black dotted lines as sort of absolute, whereas if you're in the Hartebeest-Hoek 94 datum, you are using those blue lines. And you can see that the difference between them is approximately 300 meters north-south and 70 meters or 20 meters east-west, depending on where you are. If you have a 300-meter error in South Africa or Namibia, you have probably got a datum issue. And it's the first thing to look at if you have an error. We'll have a look about how you can sort of work out and test errors using GIS later today. But that 300 meters there, 60 meters there, is a classic issue of why people drill on the wrong farm. Charles Merry has done an incredible amount of work to clarify all of this. He was, I think he still is, emeritus professor at the University of Cape Town. He is probably consulting now, and he's consulted for the Department of Lands and Surveys within South Africa. And there is his website. He developed a program called X-Form, which you can buy from him, which covers South Africa, Botswana, Swaziland, Lesotho, Zimbabwe, Namibia, and Mozambique datums and projections. And I will show you just now that program. So just as a little summary of projections and datums, there are many projections and many datums. If you have the same projection and two different datums, you will get two different sets of plane coordinates for the same points. If you've got two different projections and you've got the same datum, you will also get two different sets of plane coordinates for the same points. So knowing what your datum and knowing what your projection are vital in terms of spatial data in geosciences. Okay, how are we doing? That's not too bad. Can I stop it?